Welcome everyone. It is 3 p.m. and it's time for the Server Room Show. This is episode 73. Today I will most probably start another multi-part series, might be even 2 or even 3 parts. The topic is the story of Digital Equipment Corporation, DEC for short. It's a story or a history of a company I wanted to make it for a long time, and it really felt appropriate after the two-part episode 71 and 72, which I recorded about OpenVMS. It made sense to chronologically put this multi-part episode about Digital Equipment Corporation, which was behind VAX, VMS, OpenVMS, and also the Alpha architecture. And these are only the things I mentioned in my previous episodes. It made sense to put it here next to the episodes of after the episodes of OpenVMS. There are also a lot of great videos on YouTube, which I have linked as always in the show notes, which recollect the history of DEC and which ones I've also used as a base for the show notes and this recollection of the history of Digital Equipment Corporation, together with other sources as always, like Wikipedia, for example. I really wanted to make this a long time ago. I always put it always for later and later. This is also an episode which continues what I started to do in some of the previous episodes, that I try to see what's going on if I record these episodes only in an audio format. I don't do the usual screencast, because otherwise all you see on the screencast is my show notes, so to say, and me in the lower right corner. So I try to see what if I continue with this format where the YouTube videos are actually audiograms, which are just the audio on a fixed background and with some animation, audio waveform animation for the sound of my voice, because I think that there is not much loss of content if you don't see me, or if you don't see the show notes I'm actually reading from. So it's gonna be again an episode like that. History of Digital Equipment Corporation. Digital Equipment Corporation, DEC, was a major American corporation company in the computer industry, founded in 1957 with $7,000 US dollars of venture capital. It became the nation's second largest computer company just after IBM. Its initial major impact was in mini computers, but its later introduced VAX and Alpha systems are still notable. DEC was acquired in June 1998 by Compaq in what was at that time the largest merger in the history of the computer industry. Not long thereafter, Hewlett-Packard bought Compaq, creating a technology company second in revenue only to IBM. Aside from the company's extensive hardware and software accomplishments, it was also noteworthy for its use of matrix management. Matrix management is an organizational structure in which some individuals report to more than one supervisor or leader. Relationship described as solid line or dotted line reporting. More broadly, it may also describe the management of cross-functional, cross-business groups and other work models that do not maintain strict vertical business units or silos grouped by function and geography. The origins of DEC, Digital Equipment Corporation. Ken Olsen and Harlan Anderson were two engineers who had been working at MIT Lincoln Laboratory on the lab's various computer projects. The lab is best known for their work on what would today be known as interactivity, and their machines were among the first where operators had direct control over programs running in real time. These had started in 1944 with the famed Whirlwind, which was originally developed to make a flight simulator for the US Navy. although this was never completed. Instead this effort evolved into the SAGE system for the US Air Force, which used large screens and light guns to allow operators to interact with the radar data stored in the computer. When the Air Force project wound down, the lab returned their attention to an effort to build a version of the whirlwind using transistors in place of vacuum tubes. In order to test their new circuitry, they first built a small 18-bit machine known as TX-0, which first ran in 1956. When the TX-0 successfully proved the basic concepts, attention turned to a much larger system, the 36-bit TX-2, with a then enormous 64K words of core memory. Core was so expensive that parts of TX-0's memory were striped for the TX2, and what remained of the TX-0 was then given to MIT on a permanent loan. At MIT, Olsen and Anderson noticed something odd. Students would line up for hours to get a turn to use the strapped-down TX-0 while largely ignoring a faster IBM machine that was also available. The two decided that the draw of interactive computing was so strong that they felt there was a market for a small machine dedicated to this role, essentially commercialize the TX-0. They could sell this to users where graphical output or real-time operation would be more important than outright performance. Additionally, as the machine would cost much less than larger systems then available, it would also be able to serve users that needed a lower cost solution dedicated to a specific task where a larger 36-bit machine would not be needed. In 1957, when the pair and Ken's brother Stan went looking for capital, they found that the American business community was hostile to investing in computer companies. Many smaller computer companies had come and gone in the 1950s, wiped out when new technical developments rendered their platforms obsolete, and even large companies like RCA and General Electric were failing to make a profit in the market. The only serious expression of interest came from George Storiot and his American Research and Development Corporation. Worried that a new computer company would find it difficult to arrange further financing, Doriot suggested the fledgling company change its business plan to focus less on computers and even change their name from Digital Computer Corporation. The pair returned with an updated business plan that outlined two phases for the company's development. They would start by selling computer modules as standalone devices that could be purchased separately and wired together to produce a number of different digital systems for lab use. Then, if these digital modules were able to build a self-sustaining business, the company would be free to use them to develop a complete computer in their phase 2. The newly christened Digital Equipment Corporation received $70,000 from AR&D for a 70% share of the company, and began operations in a Civil War era textile mill in Maine and Massachusetts, where plenty of inexpensive manufacturing space was available. Digital modules. In early 1958, DEC shipped its first products, the Digital Laboratory Module line. The modules consisted of a number of individual electronic components and germanium transistors mounted to a circuit board, the actual circuits being based on those from the TX-2. The laboratory modules were packaged in an extruded aluminum housing intended to sit on an engineer's workbench, although a rack mount bay was sold that held 9 laboratory modules. They were then connected together using banana plug patch cords inserted at the front of the modules. Three versions were offered, running at 5 MHz in 1957, 500 kHz at 1959, or 10 MHz in 1960. The modules proved to be in high demand in other computer companies who used them to build equipment to test their own systems. Despite the recession of the late 1950s, the company sold 94,000 US dollars worth of these modules during 1958 alone, turning a profit at the end of its first year. The original laboratory modules were soon supplemented with the digital system module line, which were identical internally but packaged differently. The systems modules were designed with all of the connections at the back of the module using 22-pin Amphenol connectors, and were attached to each other by plugging them into backplane that could be mounted in a 19-inch rack. The backplanes allowed 25 modules in a single 5.25-inch section of rack, and allowed the high densities needed to build a computer. The original laboratory and system module lines were offered in 500 kilocycle, 5 megacycle and 10 megacycle versions. In all cases, the supply voltages were -15 and +10 volts, with logic levels of -3 volts, passive pull down, and 0 volts as active pull up. DEC used the system modules to build their memory test machine for testing core memory systems, selling about 50 of these prepackaged units over the next 8 years. The PDP-1 and LINC Link computers were also built using system modules. Modules were part of DEC's product line into the 1970s, although they went through several evolutions during this time as technology changed. The same circuits were then packaged as the first Red series flip chip modules. Later, other flip chip modules module series provided additional speed, much higher logic density, and industrial I/O capabilities. DEC published extensive data about the modules in free catalogs that became very popular. The PDP-1 family, with the company established and a successful product on the market, DEC turned its attention to the computer market once again as part of its planned Phase 2. In August 1959, Ben Gurley started design of the company's first computer, the PDP-1. In keeping with Dorio's instruction, the name was an initialism for programmable data processor, leaving off the term computer. As Gurley put it, we aren't building computers, we are building programmable data processors. The prototype was first shown publicly at the Joint Computer Conference in Boston in December 1959. The first PDP-1 was delivered to Bolt, Beranek and Newman in November 1960 and formally accepted the next April. The PDP-1 sold in basic form for 120,000 US dollars, equivalent of about 7.7 million US dollars in 2019's money. By the time production ended in 1969, 53 PDP-1s had been delivered. The PDP-1 was supplied standard with 4096 words of core memory, 18 bits per word, and ran at a basic speed of 100,000 operations per second. It was constructed using many system building blocks that were packaged into several 19-inch racks. The racks were themselves packaged into a single large mainframe case with a hexagonal control panel containing switches and lights mounted to lie at tabletop height at one end of the mainframe. Above the control panel was the system's standard input-output solution, a punched tape reader and writer. Most systems were purchased with two peripherals, the Type 30 vector graphic display and Soroban Engineering modified IBM Model B electric typewriter that was used as a printer. The Soroban system was notoriously unreliable and often replaced with a modified Friden Flexo writer, which also contained its own punched tape system. A variety of more expensive add-ons followed, including magnetic tape systems, punched card readers and punches, and faster punched tape and printer systems. When DEC introduced the PDP-1, they also mentioned large machines at 24, 30 and 36 bits based on the same design. During construction of the prototype PDP-1, some design work was carried out on a 24-bit PDP-2 and the 36-bit PDP-3. Although the PDP-2 never proceeded beyond the initial design, the PDP-3 found some interest and was designed in full. Only one PDP-3 appears to have been built in 1960 by the CIA's Scientific Engineering Institute in Waltham, Massachusetts. According to the limited information available, they used it to process radar cross-section data for the Lockheed A-12 reconnaissance aircraft. Gordon Bell remembered that it was being used in Oregon sometime later, but could not recall who was using it. In November 1962, DEC introduced the $65,000 US PDP-4. The PDP-4 was similar to the PDP-1 and used a similar instruction set, but used slower memory and different packaging to lower the price. Like the PDP-1, about 54 PDP-4s were eventually sold, most to a customer base similar to the original PDP-1. In 1964, DEC introduced its new flip chip module design and used it to re-implement the PDP-4 as the PDP-7. The PDP-7 was introduced in December 1964 and about 120 were eventually produced. An upgrade to the flip chip led to the R series, which in turn led to the PDP-7A in 1965. The PDP-7 is most famous as the original machine for the Unix operating system, and until the Interdata 8/32, Unix only ran on DEC systems. A more dramatic upgrade to the PDP-1 series was introduced in August 1966, the PDP-9. The PDP-9 was instruction compatible with the PDP-4 and 7, but ran about twice as fast as the 7 and was intended to be used in larger deployments. At only $19,900 US dollars in 1968, the PDP-9 was a big seller, eventually selling 445 machines, more than all of the earlier models combined. Even while the PDP-9 was being introduced, its replacement was being designed and was introduced as 1969's PDP-15, which re-implemented the PDP-9 using integrated circuits in place of modules. Much faster than the PDP-9, even in basic form, the PDP-15 also included a floating point unit and a separate input-output processor for further performance gains. Over 400 PDP-15s were ordered in the first 8 months of production, and the production eventually amounted to 790 examples in 12 basic models. However, by this time, other machines in DEC's lineup could fill the same niche at even lower price points, and the PDP-15 would be the last of the 18-bit series. The PDP-8 family. In 1962, Lincoln Laboratory used a selection of system building blocks to implement a small 12-bit machine and attached it to a variety of analog to digital input-output devices that made it easy to interface with various analog lab equipment. The link proved to attract intense interest in the scientific community and has since been referred to as the first real mini computer, a machine that was small and inexpensive enough to be dedicated to a single task, even in a small lab. Seeing the success of the Link in 1963, DEC took the basic logic design but stripped away the expensive analog to digital systems to produce the PDP-5. The new machine, the first outside the PDP-1 mold, was introduced at Westcon on 11th of August 1963. The 1964 ad expressed the main advantage of the PDP-5 as now you can own the PDP-5 computer for what a core memory alone used to cost, 27,000 US dollars. 116 PDP-5s were produced until the lines were shut down in early 1967. Like the PDP-1 before it, the PDP-5 inspired a series of newer models based on the same basic design that would go on to be more famous than its parent. On the 22nd of March 1965, DEC introduced the PDP-8, which replaced the PDP-5's modules with new R-series modules using flip chips. The machine was repackaged into a small tabletop case, which remains distinctive for its use of smoked plastic over the CPU, which allowed one to easily see the wire-wrapped internals of the CPU. Sold standard with 4 kilohertz of 12-bit core memory and the teletype model 33 ASR for basic input-output, the machine listed for only 18,000 US dollars. The PDP-8 is referred to as the first real mini computer because of its sub 25,000 US dollar price. Sales were unsurprisingly very strong and helped by the fact that several competitors had just entered the market with machines aimed directly at the PDP-5's market space, which the PDP-8 trounced. This gave the company 2 years of unrestricted leadership, and eventually 1,450 straight 8 machines were produced before it was replaced by newer implementations of the same basic design. DEC hit an even lower price point with the PDP-8/S, the S for serial. As the name implies, the /S used a serial arithmetic unit, which was much slower but reduced cost so much that the system sold for under 10,000 US dollars. DEC then used the new PDP-8 design as the basis for a new Link, the 2 processors Link 8. The Link 8 used one PDP-8 CPU and a separate Link CPU, and included instructions to switch from one to the other. This allowed customers to run their existing Link programs or upgrade to the PDP-8 all in software. Although not a huge seller, 142 Link 8S were sold starting at 38,500 US dollars. Like the original Link to PDP-5 evolution, the Link 8 was then modified into the single processor PDP-12, adding another 1,000 machines to the 12-bit family. Newer circuitry designs led to the PDP-8-I and the PDP-8-L in 1968. In 1975, 1 year after an agreement between DEC and Intersil, the Intersil 6100 chip was launched, effectively PDP-8 on a chip. This was a way to allow PDP-8 software to be run even after the official end-of-life announcement for the DEC PDP-8 product line. I have roughly 5 minutes left, and I would like not to start the next part, which is the PDP-10 family, but you know what, actually I think we have time for that. The PDP-10 family, while the PDP-5 introduced a lower cost line, 1963's PDP-6 was intended to take DEC into the mainframe market with a 36-bit machine. However, the PDP-6 proved to be a hard sell with customers, as it offered a few obvious advantages over similar machines from the better established vendors like IBM or Honeywell, in spite of its low cost around 300,000 US dollars. Only 23 were sold, or 26 depending on the source, and Unlike other models, the low sales meant the PDP-6 was not improved with successor versions. However, the PDP-6 is historically important as the platform that introduced the Monitor, an early time-sharing operating system that would evolve into the widely used top stand. When newer flip chip packaging allowed the PDP-6 to be re-implemented at a much lower cost, DEC took the opportunity to refine their 36-bit design, introducing the PDP-10 in 1968. The PDP-10 was as much as a success as the PDP-6 was a commercial failure. About 700 mainframe PDP-10s were sold before production ended in 1984. The PDP-10 was widely used in university settings and thus was the basis of many advances in computing and operating system design during the 1970s. DEC later rebranded all of the models in the 36-bit series as the DEC System 10, and PDP-10s are generally referred to by the model of the CPU, starting with the KA10, soon upgraded to the KI10, I standing for Integrated Circuit, then to KL10, L as in large-scale integration, ECL logic. Also the KS10 as for a small form factor. Unified product line upgrades produced the compatible DEC System 20, along with the TOPS 20 operating system that included virtual memory support. The Jupyter project was supposed to continue the mainframe product line into the future by using gate arrays with an innovative air mover cooling system coupled with a built-in floating point processing engine called FBox. The design was intended for a top-tier scientific computing niche, yet the critical performance measurement was based upon COBOL compilation, which did not fully utilize the primary design features of Jupyter technology. When the Jupyter project was cancelled in 1983, some of the engineers adopted aspects of the 36-bit design into a forthcoming 32-bit design, releasing the high-end VEX 8600 in 1985. This is where we gonna leave this part 1 episode of the history of digital equipment workstation, and we will continue next Saturday part 2 with things like deck tape, the magnetic disk storage, the PDP-11 finally, and talking about other achievements like the VAX and the early microcomputers of Digital Equipment Corporation, a little bit of the VAX Mate, DEC Professional, and let's see if everything can be fitted into the second part of this episode, or perhaps I need to do a part 3 as well. Thank you very much for listening, and see you next Saturday.